Our sun is a colossal ball of hydrogen and helium, 330,000 times the mass of Earth. It sits at the gravitational heart of our solar system, holding everything from rocky inner planets to distant icy bodies in its eternal embrace. But the sun's role goes far beyond mere gravity. Every second, thanks to the nuclear fusion reactions blazing away in its core, it generates a gargantuan 386 trillion joules of energy, an almost incomprehensible figure that dwarfs anything human civilization has ever produced. Of that staggering output, 175 quadrillion joules reaches the Earth every single second in the form of sunlight, streaming across 150 million kilometers of empty space before warming our atmosphere and illuminating our world. It is this radiation that provides pretty much all the energy we use as humans on Earth. Sunlight underpins food chains, fueling the photosynthesis that sits at the base of nearly every ecosystem on the planet. It drives the weather systems and temperature gradients we harness for wind and solar renewables. And of course, it is sunlight captured by ancient plants hundreds of millions of years ago, compressed and transformed deep within the Earth's crust over geological timescales that we are still utilizing every time we burn fossil fuels. In a very real sense, almost every joule of energy our civilization runs on is borrowed sunshine. But what if there was a different way to power our modern industrialized society? What if, instead of depending on photons that have already made their long journey across 150 million kilometers of space, we could recreate the very nuclear fusion reactions that keep our sun burning right here on Earth? What if we could bottle that same fundamental process, that collision of atomic nuclei under extreme heat and pressure that has powered stars for billions of years, and use it to grant us an unending source of clean, safe, and extraordinarily efficient power? What if, in other words, we could make a star on Earth? Before we start, I want to tell you something. A lot of strange things have been happening in space lately, so subscribe to this channel right now, and I'll tell you even more secrets of space. And write in the comments below what you think about all of this. 41. Humanity, it seems, has a power problem. Even as we burn through our dwindling fossil fuel reserves, and climate chaos intensifies all around us, every year our energy requirements rise by an estimated 1 to 2%. The consequences of this relentless growth are hard to overstate. Grids strain under increasing demand, nations compete for shrinking resources, and the carbon we pump into the atmosphere accumulates faster than any natural process can absorb it. The need for a clean, efficient, and inexhaustible energy source has never been so acute. For many decades, this has been the promise of nuclear fusion. Unlike nuclear fission, which splits large, rare, and unstable isotopes to generate power, fusion technology aims to replicate the processes that happen inside our sun, fusing hydrogen into helium and releasing a tremendous amount of energy in the process. The appeal is obvious. The fuel is virtually limitless. The reaction produces no long-lived radioactive waste, and the energy yield dwarfs anything achievable through conventional combustion. Yet, since fusion was first talked about as a serious contender for energy generation in the 1950s, it has become a cliché that it is perpetually 30 years away from becoming reality. Decade after decade, the promise has remained tantalizingly close and yet stubbornly out of reach. So, why does fusion seem always just beyond our grasp? And do the new private enterprises that have recently entered the field really offer any hope of shaking things up? To begin to answer these questions, there is no better place to start than the place that inspired fusion science in the first place: our sun. As strange as it sounds today, at the turn of the last century, we simply did not know what powered the sun. The source of the heat and light that sustains all life on Earth was a genuine mystery. The leading theory was that the sun's energy came from gravitational contraction. The idea proposed that as a star gradually radiates energy into space, it cools and collapses further under its own gravity, which in turn causes gravitational potential energy to be converted into heat deep in the star's core. We now know that gravitational contraction is a real and measurable process. It plays a central role in the formation of stars, and it is also the reason that the gas giant Jupiter radiates more energy to space than it actually receives from the sun. In fact, Jupiter is shrinking by roughly 2 centimeters every year under its own gravity. And as the resulting internal heat works its way up from deep within the planet's interior and escapes into space, it drives the colossal swirling storms that dance across the planet's surface. But when it comes to powering a star over billions of years, one scientist realized that contraction simply did not stand up to scrutiny. In a landmark 1920 paper, the physicist Arthur Eddington wrote that if the contraction theory were proposed that day as a novel hypothesis, he did not think it would stand the smallest chance of acceptance. He argued that contraction alone would be hopelessly inadequate for powering a body that radiates as much energy as our sun does, continuously, across geological timescales stretching back billions of years. The numbers just did not work. Suspecting that stars were places in which hydrogen atoms were somehow cobbled together into heavier elements, Eddington proposed a fundamentally different source of energy. Drawing on experiments carried out by his fellow scientist Francis Aston, Aston had made a precise and striking observation. The mass of a helium nucleus was ever so slightly less than the combined mass of 4 individual hydrogen nuclei. So, if a helium atom was essentially 4 hydrogen atoms fused together, a small but measurable amount of mass appeared to go missing in the process. Eddington believed that this missing mass was being converted directly into energy according to Einstein's famous equation, E equals mc squared. And because c, the speed of light, is such an extraordinarily large number, the energy released from even a tiny loss of mass is immense. Fusing hydrogen into helium would therefore liberate more than enough energy to account for everything the sun radiates across its entire lifetime. Eddington's ideas were bold and largely unproven at the time, but they soon inspired serious theoretical work. In 1929, the first detailed calculations of stellar nuclear fusion were published by Robert Discourse Atkinson and Fritz Houtermans. Their work confirmed what Eddington had suspected. The sun, and indeed all stars, were essentially giant natural fusion reactors, taking the most abundant element in the universe, hydrogen, and fusing it into progressively heavier elements, beginning with helium. Replicating this process on Earth would be enormously advantageous, particularly when compared with nuclear fission, the process used in the nuclear power plants we operate today. Fission relies on splitting large, rare, and unstable isotopes, such as uranium-235 and plutonium-239, materials that must be carefully mined, enriched, and handled throughout their long and hazardous life cycles. Stellar nuclear fusion, by contrast, relies on hydrogen, an element that is effectively boundless on Earth and can be obtained through the straightforward electrolysis of seawater. And unlike the radioactive byproducts of fission that create a massive and enduring disposal problem for modern nuclear power stations, waste that can remain dangerously active for tens of thousands of years, the primary byproduct of stellar fusion is helium, an extraordinarily useful and increasingly valuable element. Thanks to its exceptionally low boiling point of just 4 degrees above absolute zero, helium is indispensable for cooling the superconducting magnets in MRI machines, keeping them at the temperatures required for zero electrical resistance. It plays the same critical role in large-scale scientific research infrastructure like CERN, where it cools the enormous electromagnets of the Large Hadron Collider, and it is equally essential in the production of microchips, where it helps manage heat during the manufacturing process. Far from being a waste product, helium is a strategic resource that modern civilization genuinely depends on and needs more of, making fusion's promise of generating it in abundance all the more appealing. So, how exactly do stars achieve this extraordinary alchemy of fusing hydrogen into helium? And how are scientists going about trying to replicate that process here on Earth? The first thing to consider is the reaction medium, the stuff that stars are actually made of. Unlike matter on Earth, stars are not composed of conventional atoms and molecules, where negatively charged electron clouds orbit positively charged nuclei in stable, well-defined arrangements. Stars are so extraordinarily hot that electrons are stripped away from their parent atoms entirely, liberated from their orbitals by the sheer thermal energy of the environment. The resulting soup of charged particles, ions and free electrons moving at tremendous speeds, is known as plasma. And it is within plasma that nuclear fusion can take place. Plasma is by far the most common state of matter in the universe, making up well over 99.9% of all visible non-dark matter. Stars, nebulae, and the vast filaments of the interstellar medium are all plasma. We, however, are part of the remaining 0.1%, that small and cosmically unusual pocket of the universe that is cool enough for electrons to remain confined to atomic orbitals, and where chemistry, rather than nuclear physics, dominates the behavior of matter. This relatively temperate corner of existence is what allows cool balls of rock covered in liquid water, like Earth, to form and persist. For us, recreating the conditions that come naturally to stars, generating plasma hot enough to sustain fusion, and then containing it long enough to harvest energy, is a considerable engineering and scientific challenge. The sun has one quite literal giant advantage on its side: sheer mass. It is so enormous that its own gravitational force holds the plasma in a near-perfect sphere, with pressure at its core reaching around 150 grams per cubic centimeter. So extraordinarily dense that a single teaspoon of that material would weigh close to a kilogram. The biggest fusion reactor on Earth, ITER in the south of France, is a leading international project involving 35 nations that hopes to be operational in 2034. In stark contrast to the Sun, it will use just a few grams of plasma material contained within a chamber of 830 cubic meters. Because the plasma inside ITER is under such comparatively low pressure, particles are simply not squeezed together the way they are deep inside the Sun. It has to be driven to far higher temperatures to achieve the same fusion conditions. We are talking about 150 million degrees Celsius, compared to the roughly 15 million degrees found at the Sun's core. Counterintuitively, making fusion work on Earth requires temperatures 10 times hotter than those found at the heart of a star. Fairly obviously, you cannot hold a material at 150 million degrees inside a container made of conventional matter. If the plasma contacted the walls, even momentarily, it would rapidly cool, electrons would condense back into atomic orbitals, and it would cease to be plasma altogether. And it almost goes without saying that the container itself would be catastrophically, irreparably damaged in the process. The plasma therefore has to be isolated in a vacuum, kept entirely clear of any solid surface. Two broad approaches have been developed to achieve this. The first is magnetic confinement fusion. Because plasma is a soup of charged particles, positively charged ions and negatively charged free electrons, it responds strongly to magnetic fields, which can exert force on moving charges and redirect their paths. Magnetic confinement fusion takes direct advantage of this property, using a carefully arranged ring of extremely powerful magnets to hold the plasma in a continuous donut-shaped configuration in which fusion can take place. There are several different design variants, including stellarators and reversed field pinch devices, but the leading and most developed design is called the tokamak, a word derived from a Russian acronym for toroidal chamber with magnetic coils. The tokamak is the design that will be used at ITER. The second approach, inertial confinement fusion, takes its conceptual inspiration from a rather different source: thermonuclear bombs. Rather than holding plasma in a stable, sustained configuration, it works by firing an intense burst of lasers or high-velocity projectiles at a small pellet containing fusion fuel, compressing and heating it so rapidly and violently that it briefly reaches the conditions required for fusion. The goal is to create a tiny, transient blob of plasma that releases a pulse of fusion energy over just a few nanoseconds before the plasma dissipates and the reaction extinguishes itself. Both of these approaches represent immense engineering challenges. Magnetic confinement, fusion requires vast and continuous supplies of electricity to power its magnets, while inertial confinement fusion demands even larger, carefully timed pulses of electrical energy drawn from banks of capacitors. In both cases, the difficulty is not just igniting fusion, but doing so in a way that produces more energy than the process consumes. But not only do the huge amounts of power involved put tremendous strain on components, which have to be replaced frequently, it means that for a reactor to be viable, the energy obtained from the fusion reaction must exceed the colossal amount of energy required to initiate it. A considerable challenge that engineers and physicists continue to wrestle with today. You might think, surely once you have surpassed this feat, once you've got more energy out than you put in, that would be it. A huge win, the moment the world has been waiting for. After all, the fuel, hydrogen, is both cheap and extraordinarily abundant. It is essentially the most common element in the observable universe, and here on Earth, it can be extracted from seawater in vast quantities. So, what's the problem? But alas, it is not that simple. And to understand why, we have to look back once again at our star and the fusion reactions that only take place deep inside the stellar core, under conditions of almost unimaginable pressure and temperature. It is here in the Sun's core that hydrogen is fused into helium via a multi-step reaction. Firstly, two hydrogen nuclei, or single protons, combine, with one undergoing a process called beta decay, to transform it into a neutron. This transformation is subtle but essential, because a nucleus made of two protons alone would be unstable and fly apart almost instantly. The resulting neutron-proton pair is a nucleus of a heavy isotope of hydrogen known as deuterium, sometimes called heavy hydrogen, which is stable and can participate in further reactions. In the next step, another proton combines with the deuterium nucleus to generate a helium-3 nucleus, which contains two protons and one neutron. In the final step, Two of these helium-3 nuclei fuse together to produce a helium-4 nucleus containing 2 protons and 2 neutrons, also known as an alpha particle, along with 2 free protons that are released back into the plasma to potentially begin the cycle again. Now, this may sound fairly straightforward, but it's not. The reason being that even in the Sun, getting 2 protons to react to form deuterium in the very first step of the reaction is far from easy. It is, in fact, one of the most improbable events in all of physics. For 2 protons to fuse, they must get extremely close to each other, around 10 to the power of -15 meters apart. Only at this extraordinarily tiny distance does the strong nuclear force kick in, the force that holds protons and neutrons together inside the nucleus of an atom, pulling them toward each other and binding them. However, for 2 positively charged protons, getting this close means overcoming an immense amount of electrostatic repulsion, the natural tendency of like charges to push each other away with great force. So much so that even the kinetic energy provided by the extreme conditions at the heart of the Sun, where protons are traveling at around 500 kilometers per second in a roiling plasma of tens of millions of degrees, is wildly insufficient. In fact, protons possess only around 1,000th of the kinetic energy they would need to classically overcome this electrostatic barrier. It turns out the only reason the Sun is able to sustain fusion at all is because quantum effects come into play. According to quantum physics, protons don't just behave as particles, they also behave as waves, with a spatial probability distribution that is smeared out rather than pinned to a precise location. This wave behavior means that in roughly 10 to the power of 28 proton-proton interactions, the protons can effectively overcome this energy barrier, getting close enough that the strong nuclear force pulls them together. This phenomenon is called quantum tunneling, and without it, our Sun would simply go dark. But even when protons are drawn together this way, there is yet another hurdle to contend with. The force that mediates the conversion of one of the protons into a neutron is called the weak force, which, because it operates through the exchange of the very massive W boson, is extraordinarily inefficient. This leads to the more likely outcome of a proton-proton interaction being a short-lived proton pair, known as a diproton, which almost immediately becomes unstable and decays back into 2 individual protons. Together, these effects mean that the rate at which protons successfully fuse in our star is almost incomprehensibly slow. On average, a single proton will wait around 10 billion years before finally undergoing fusion, longer than the current age of the universe. Indeed, the only reason the proton-proton reaction proceeds at all is because there are an almost unfathomable number of protons packed into the Sun, allowing it to convert around 600 million tons of hydrogen into roughly 596 million tons of helium every second, with the missing mass being released as the energy that lights and warms our world. This sounds like a staggering throughput, but it is actually only a tiny fraction of the total hydrogen available for fusion. Pausing for a moment to consider the big picture, this is very good news for us Earthlings. It means instead of annihilating itself in a giant thermonuclear explosion, the Sun has been gently burning through its hydrogen stocks for around 4.6 billion years, and will continue doing so for at least a few billion more. It's only because protons are so extraordinarily slow at converting into deuterium that we are here at all. That cosmic inefficiency is, paradoxically, the very thing that made complex life possible. For fusion on Earth, on the other hand, this is deeply bad news. It means the probability of proton-proton reactions happening, where we have vastly less plasma and vastly less time to work with, is essentially zero. Indeed, the reaction has never once been experimentally measured in a laboratory setting, and that absence speaks volumes. In fact, looking at the problem in the most basic and fundamental way, it is statistically impossible to achieve proton-proton fusion on Earth in any meaningful sense. So, what are all these fusion researchers actually doing? Why do we even bother trying? Well, they are not attempting to fuse protons at all. Instead, they are trying to fuse alternative combinations of nuclei that are far more chemically reactive and far more willing to interact under conditions we can actually create and sustain. Back in the 1930s, Mark Oliphant, a young student working under the legendary Ernest Rutherford, conducted a landmark series of experiments. He fired deuterium nuclei at one another, generating a range of exotic hydrogen and helium isotopes in the process, and thus proved definitively that heavy hydrogen nuclei could be made to react with one another under the right circumstances. It was a foundational moment in nuclear physics. Today, fusion scientists favor a particular combination that was first put to destructive use in the hydrogen bomb, one that is an almost incomprehensible 24 orders of magnitude more reactive than protons alone. That combination is deuterium and tritium. Deuterium, the classic heavy hydrogen, consists of one proton and one neutron bound together in the nucleus. Tritium is the even heavier isotope of hydrogen, carrying one proton but two neutrons. The reason this pairing is so dramatically more reactive comes down to nuclear physics. Those extra neutrons produce a greater strong nuclear force binding the nuclei together, and crucially, there is no need for one proton to undergo the agonizingly slow, weak force-mediated beta decay into a neutron that bottlenecks the proton-proton chain in the Sun. Deuterium and tritium aren't just more reactive than the protons that power the Sun. They also give rise to entirely different reaction products. Instead of generating an alpha particle and two protons as the solar chain does, the deuterium-tritium reaction produces an alpha particle and a high-energy neutron. And like the proton-proton reaction chain, it still releases an enormous amount of energy that we can harness to generate electricity. To put the scale of that energy density in perspective, just 1 gram of deuterium-tritium fuel holds energy equivalent to around 2,400 gallons of oil. So if we've identified more reactive starting materials that yield plenty of energy output, what's the problem now? Well, it isn't just one problem, it's a cascade of them. Let's start with those neutrons. Being considerably lighter than alpha particles, the neutrons carry away the majority of the energy released in the fusion reaction, which means they absolutely have to be captured and put to work if we want to extract any useful power. But controlling a subatomic particle that carries no electrical charge whatsoever is no small feat. Neutrons are completely unaffected by the powerful magnetic fields that contain and shape the plasma, and so they stream outward from the reactor in all directions, at roughly 1/6 the speed of light. To deal with this, most reactor designs incorporate what's called a blanket, a thick layer of material surrounding the reaction chamber that is specifically engineered to absorb those high-energy neutrons and convert their kinetic energy into heat. That heat can then be used to generate steam, drive a turbine, and ultimately produce electricity. But this approach is far from a clean solution. Neutrons don't simply stop politely in the blanket. They scatter and ricochet throughout the entire reactor structure, damaging virtually everything they strike at the atomic level. This bombardment causes progressive material degradation that severely limits the operational lifespan of many critical components, and particularly the reactor walls themselves. Another significant issue stems from the reactants. While deuterium is relatively abundant in nature, being readily extracted from ordinary seawater and cheap at around $13 a gram, tritium is neither abundant nor cheap. It is a radioactive isotope with a half-life of just 12.3 years, meaning it is constantly decaying away. And the only commercial sources on Earth are Canada's 19 deuterium-uranium CANDU nuclear reactors, each of which produces just half a kilogram of tritium annually as a byproduct. ITER, the International Fusion Project in France, estimates that a commercial fusion power plant would require approximately 125 kilograms of tritium per year to operate. Current global tritium reserves sit at around just 25 kilograms in total, and with roughly half of Canada's CANDU reactors due to be decommissioned within this decade, that already tiny reserve is quite literally going to decay away faster than it can be replenished. Scientists, however, do have a potential solution waiting in the wings for the tritium supply problem. As well as carrying energy out of the reactor, those high-energy neutrons produced by deuterium-tritium fusion can be used for something called tritium breeding. The idea is that you surround the reactor with a blanket material, a thick layer of substance specifically chosen because it generates tritium when bombarded by neutrons. The substance preferred by most fusion researchers is lithium, which upon absorbing a neutron helpfully decays into a helium atom and a tritium nucleus. It's an elegant solution in principle. The very neutrons your reactor produces become the raw material for replenishing your fuel supply. However, as ever in fusion, this solution comes with its own problem. If each deuterium-tritium fusion reaction generates one neutron, which, via lithium, can be used to generate one new tritium atom, you would need to operate at an impossible 100% efficiency to prevent your tritium supply from slowly and inevitably dwindling. Every neutron lost to the walls, to instrumentation, to any material that doesn't happen to be lithium, is a tritium atom you'll never see. In a real reactor, losses are everywhere. The answer most fusion researchers favor is to add layers of other elements like beryllium that can act as neutron multipliers, absorbing one incoming neutron and releasing two in its place, effectively amplifying the neutron population and giving the lithium blanket more raw material to work with. But not only is beryllium toxic to handle and notoriously difficult to work with safely, it is also in relatively short supply globally, And natural beryllium is contaminated with trace amounts of uranium. When that uranium is bombarded with neutrons inside a reactor environment, it produces radioactive byproducts that complicate the entire waste picture. Less than ideal, to put it gently. And regardless of which neutron multiplier strategy you choose, there are serious concerns among researchers that, even with breeding, most reactor designs would struggle to generate enough tritium over their operational lifetime to be truly self-sustaining and commercially viable. The numbers are tight, and tight numbers in engineering tend to mean trouble. So at this point, you might be thinking, hang on a minute. It seems like a lot of the touted advantages of fusion, the promise of bountiful clean energy, plentiful and easily sourced starting materials, innocuous or even useful byproducts, are kind of falling away one by one. Well, you'd be right. We're not fusing hydrogen in the simple, abundant form that a star fuses deep in its core. We're relying on tritium, a rare and radioactive isotope that barely exists in nature. And we're not producing just helium as a clean end product, but a collection of other radioactive materials generated by neutron bombardment of the reactor's own structure over time. The simple truth, no matter what the headlines say, is that we cannot make a star on Earth. Stars fuse ordinary hydrogen because they have the luxury of almost incomprehensible mass, gravitational pressure, and billions of years of patience. We have none of those things, so we take shortcuts. And those shortcuts, relying on tritium, on immense magnetic fields, on materials science at the edge of what's possible, create a world of cascading engineering challenges. This is why, since the first fusion reactor patent was granted in 1946, fusion has always seemed to sit just out of reach, tantalizingly close, but never quite there. Each solution that researchers devise tends to introduce a new set of problems that then require their own solutions. But not all hope is lost. In recent years, things do seem to be genuinely changing, driven by some hugely significant scientific breakthroughs that have shifted the mood in the fusion community. In December 2022, for the first time in the long history of fusion research, more energy was extracted from a fusion reaction than was required to initiate it. A milestone known as ignition, a challenge that had eluded researchers for decades and that many had begun to wonder whether it was even achievable within a human lifetime. At the National Ignition Facility, a research-scale inertial confinement fusion reactor in California, 3.15 megajoules of energy were obtained from a tiny pellet of deuterium-tritium fuel, using an energy input of just 2.05 megajoules. The margin was modest, but the principle was proven. Then, in late 2023, the experimental jet reactor in the United Kingdom, a tokamak design that had been operating for decades as a testbed for fusion science, generated a world record 69 megajoules of energy from just 0.2 milligrams of deuterium-tritium fuel, a figure that underlined just how extraordinarily energy-dense fusion reactions are, even if the engineering challenges of capturing and using that energy reliably remain formidable. And while international behemoths like ITER inch closer to operation, a flurry of private investment has also entered the field, exploring alternative fusion technologies. One prominent example is the Massachusetts-based Commonwealth Fusion Systems, backed by Google, NVIDIA, and Bill Gates. Rather than following the conventional path of large-scale tokamak construction, CFS proposes using high-temperature superconducting magnets to produce a far more compact tokamak design. These advanced magnets generate substantially stronger magnetic fields than traditional superconductors, allowing the plasma chamber to be shrunk considerably, without sacrificing confinement quality. CFS claims it will have a commercial plant online by the early 2030s, a timeline that, if met, would mark a watershed moment for the entire industry. Another outfit, based out of Washington State, called Helion, believes it is going to get there even earlier. Backed by the likes of Sam Altman, this company has taken a completely new approach to reactor design altogether. Rather than holding plasma in a steady magnetic bottle the way a conventional tokamak does, Helion fires two rings of plasma together at over 1 million kilometers per hour to generate fusion conditions, a kind of halfway house between magnetic confinement and inertial confinement, borrowing elements from both without committing fully to either. This approach opens up an unusual and potentially transformative fuel choice. It allows the reactor to fuse deuterium, not with tritium, but with a reactive isotope of helium known as helium-3, doing away with the problematic tritium fuel entirely. The use of helium-3 is central to Helion's entire strategy because the physics of the reaction work out very differently from the deuterium-tritium pathway that most fusion programs rely on. Instead of producing an alpha particle and a high-energy neutron, a deuterium and helium-3 reaction generates an alpha particle and a proton. That distinction turns out to be vitally important. Because a proton carries an electric charge, it responds to magnetic fields and stays within the plasma rather than escaping the reactor. This means there is no neutral particle whizzing off out of the containment vessel, carrying the bulk of the reaction energy with it. Instead, the energy is retained within the plasma itself. As the fusion reactions proceed, that energy creates a rise in internal pressure and a corresponding change in the surrounding magnetic field. That magnetic flux change can be harvested to generate electricity directly, with no Victorian steam turbines involved at all. It is an elegantly direct conversion of fusion energy into electrical power. So, what is the catch, you may rightfully ask? Well, just like tritium, helium-3 is extraordinarily rare on Earth, and it also has to be bred rather than simply mined or purchased. In Helion's case, helium-3 is produced through a deuterium-deuterium fusion reaction. And frustratingly, this breeding process does generate those reactor-damaging neutrons that the main deuterium helium-3 cycle was specifically designed to avoid. One of Helion's proposed solutions to this dilemma is to separate the two reactions entirely, operating commercial power plants on deuterium helium-3 fuel while running dedicated feeder reactors whose sole purpose is manufacturing helium-3. These feeder reactors would be designed with deliberately shorter planned lifespans, accepting the neutron damage as a manageable trade-off given their more limited role. But there is another significant hurdle with deuterium helium-3 as a fuel mixture. It requires substantially higher plasma temperatures and fuel densities than conventional deuterium-tritium fuel to reach ignition conditions. Enormous pulses of electricity are needed each time the reactor fires in order to generate those conditions, placing immense strain on both the electricity supply infrastructure and the reactor components themselves. Managing those repeated high-energy shocks without degrading critical hardware is a considerable engineering challenge that Helion must overcome as the company embarks on building its first commercial-scale reactor. Nevertheless, CEO David Kirtley claims this plant will be online and supplying power to Microsoft data centers by 2028. Whether or not any of this comes to pass, only time will tell. However, even if none of these private ventures manage to hit their well-publicized milestones, the mere fact that this level of investment exists at all is deeply telling. It reflects the remarkable moment the fusion sector currently finds itself in, one defined by genuine momentum rather than perpetual promise. With powerful new algorithmic and artificial intelligence tools now at their disposal, many researchers and engineers working in the field genuinely feel that fusion is finally inching closer to reality in a way that previous generations could only theorize about. The computational power alone to model plasma behavior, optimize magnetic confinement, and simulate complex engineering scenarios at speeds that would have seemed impossible even a decade ago has meaningfully changed what progress looks like day to day. And though significant unsolved scientific and engineering challenges remain, regardless of which technological approach you favor, the sheer diversity of fusion concepts now being actively pursued is itself a considerable asset. Where once the field was dominated by a single dominant paradigm, today there are tokamaks, stellarators, inertial confinement systems, compact high-field devices, and more exotic configurations all advancing in parallel. That breadth increases the collective odds that at least one path leads somewhere transformative. So, while we will never truly recreate a star on Earth, the physics simply won't allow it at that scale. It is very possible that one, or even several, of the approximations we are working so hard to build will play a pivotal role in the energy landscape of the future, a future that faces urgent and mounting pressure to decarbonize its power supply. It feels right to end by returning to Arthur Eddington and his remarkably prescient 1920 musings on the nature of the energy that powers stars. Over a century ago, before fusion was even a fully formed scientific concept, he wrote, "A star is drawing on some vast reservoir of energy by means unknown to us. This reservoir can scarcely be other than the subatomic energy which, it is known, exists abundantly in all matter. We sometimes dream that man will one day learn how to release it and use it for his service. The store is well nigh inexhaustible, if only it could be tapped. Maybe, finally, it won't be another 30 years until we find out if it can." That's all for today. If you like space stories and want to stay up to date with new episodes, subscribe to this channel and turn on notifications. See you in the next podcast.